So yeah, just great to see everyone. So I'll just hop right into it. As Adam said, I'm kind of a data engineer at monster.com. That's Monster, the job search site, not Monster, the energy drink. I have had people get that mixed up before, believe it or not. Then they're really confused when I talk about machine learning and data, because I guess that would be weird for an energy drink. But anyways, so one of my major interests is kind of looking at the deploying, taking deep learning models and using them in a production setting and using them in industry. And right now there's kind of a lot of barriers to doing that. Some of the barriers are related to data, and specifically not having a lot of annotated data. And obviously for those kinds of things you'd use transfer learning, meta learning, other things. There's also code quality barriers, which is one of the things I'm going to be talking tonight. Oftentimes you get these research papers, and even when the authors release the code, the research paper or code is very hard to refactor, very hard to use in an actual kind of industry setting, because it's very hard to extend to new data sets. There's of course the interpretability problem you probably all heard of. Deep learning is kind of a black box. You can't really do much for stakeholders. Then there's also this problem of deep learning is very brittle. There's a lot of hyperparameters to track, a lot of optimizers to use, and if you don't get stuff exactly right and effectively track all these things, it's going to be very hard to get a good result. Finally, deep learning models in general are just very hard to deploy. So even though I'm going to be focused just primarily on just those 2 points, I really think those 2 highlight points are important for the other 3 as well. For instance, good model code quality makes it easier to do transfer learning and meta learning, as I'll show a brief example of. Similarly, better tracking of hyperparameters and what layers exactly you're freezing for transfer learning, or what tasks you're using for transfer learning makes it a lot easier to gauge which types are effective. Similarly, even on interpretability, if you've effectively tracked your experiments, it's much easier to, for instance, run a perturbation experiment where you say just perturbate the model, or don't include some data, or cut out various neurons in the neural network. And it's also very easy, for instance, if your model code quality is good, to then extract feature weights and various activation functions, various heat diagrams, and also model weights.
So can you just describe transfer learning a little bit for some of the audience who might not?
Okay, so yeah, transfer learning is essentially the idea is if you train on a related task, even if you don't have too much data, I'll talk about a bit more later, is if you train on a very large annotated data set, even if it's not the data set you're trying to do predictions on, then the model can essentially learn from that data set, and then you'll fine tune it onto your target data set, which might be a very small data set. So the idea is the neural network, or whatever model you're using, will learn general patterns on the large data set, and then you can fine tune it for specific patterns on your small data set. And I will go into that in more detail, but I just did want to keep things moving. So, and finally, on the last point, you obviously can't deploy something you can't reproduce. If your code quality is very bad, then it's going to be almost impossible to deploy, to refactor for deployment and inference speed and all those types of things. So number running theme throughout the night. I've seen a lot of people questioning whether software engineering best practices are really necessary for data science and AI. I hear various things like this will never make it to production, this is just exploratory analysis. But one of my major thesis for tonight is, particularly in the case of machine learning, good code quality is what's going to enable reproducible experiments, and moreover extendable experiments. I too often see data scientists clothesline themselves with bad code quality when you don't need to be. Instead, it's much more effective to have clean, nice quality code, and it will help you collaborate and achieve your goals. So moving on to reproducibility, you probably all heard about the quote-unquote reproducibility crisis in machine learning. I won't spend too much time describing that, but obviously if you can't simply put, if you can't reproduce your experiments, then people don't know if they're valid to begin with. So reproducibility is very important, for it's kind of the benchmark of science. So further, why do we want to design for reproducibility? Obviously, it requires initial overhead, which can sometimes be tedious. I know that all too well, but it's my firm belief once you overcome that initial overhead, then you'll start to see much faster experiments turnover times. For instance, it's a lot easier to collaborate on a very clean, high quality code base than it is to pull someone into a messy code base. Secondly, it's also very, hard to extend to new data sets when your code quality is poor and your experiments aren't reproducible and you don't have good baseline benchmarks. Finally, I see this a lot. People put their code aside for several months and then they return several months later and they have almost no idea what they were doing and they take another 2 weeks just to ramp up and remember what they're doing. There's a really good LNNLP slide deck on this. I won't go into that now, but I am going to post my slides later so you can follow all these links if you want. Okay, my personal experience, I unfortunately am all too familiar with this. One of my research projects I wanted to originally do was use transfer learning on medical image data. So I wanted to take chest x-rays and essentially automatically localize nodules, pneumonia, other conditions in them, but I didn't have a lot of annotated data. So my idea was to use transfer learning and use an object detector, trained on various detecting cars, planes, everyday objects, bottles, cans, other things, because there was a lot of annotated data on that. Like a lot of you, I decided to use a Jupyter notebook. Well, actually it was a Google Collaboratory notebook, but essentially the same thing, and it just turned into this absolute mess. Obviously you can't see this here, but midway through, I wasn't really keeping track of version numbers of code, so the actual RetinaNet detector, there was a big update to the repository, and then I could no longer load my previous weights and my previous training sessions. I tried to retrace the commit hashes, but it just in the end didn't really work. I obviously did split my data into train, test, and validation, but I had all these different ways of commenting in and out data. I had no central way of essentially managing my data per experiment, so it got very messy. Another problem was I couldn't keep track of which results, which frozen layers, which learning rates corresponded to which model weight files. That might not seem important, but when you get hundreds of model weight files and you can't associate any of them with the actual training parameters, then you're basically doomed. And finally, a lot of people probably do this, I just kind of naively, print out my results and copy them to an Excel spreadsheet. There's nothing in theory wrong with doing this, but when you have this type of complexity, it becomes very hard and you need to be very diligent in order to not kind of mess up how you're reporting your results. So in summary, I still think this was a really good idea. There have been many very successful, yeah.
Is this the NIH public X-ray data set for that?
Oh yeah, it's the ChexNet.
One of the worst problems that you started with was the data itself was incorrectly labeled, but a lot of data was inspecific.
Yeah, that was definitely a problem too. But yeah, I was actually using the bounding box subset of that. So yeah, that too. But yeah, basically, I still think transfer learning in medical imaging has proven highly successful, so I don't think the idea was totally flawed, at least. I didn't devote enough time to, hyperparameter management, effective tracking of experiments, and all these other things. In the end, it resulted in my paper getting rejected several times and me just canning the whole project eventually. So my lesson for tonight is don't be like me, or at least how I used to be. So what I'm just going to go over tonight is starting with coding style and code quality, then go on to parameter management, then go on to data management, and then finally dependency management. So I'll just jump right into this. First point, use type hinting and document strings. We all know Python is dynamically typed, and why that's nice in some cases, it causes massive headaches in others. For instance, particularly in the machine learning case, we're often passing around NumPy arrays, tensors, data frames, and if we don't have type hints and when we don't have document strings, we have no idea which are which unless we basically run through the code and do a bunch of print statements. And then without document strings in particular in deep learning, you have no idea what the shapes are. So let's look at a quick case study. I hope everyone can see this okay. So even though this code is actually reasonably clean, you probably have no idea what's going on here. And even someone who knows PyTorch probably will take 10 or 15, maybe even 20 minutes to really get a sense, and they'll probably have to run multiple print statements. Why is that? I mean, first of all, we have no idea what X is. We don't know if it's a tensor, a NumPy array, or something else. Really, if you know PyTorch, you could probably guess it's a PyTorch tensor, but even that's not 100% certain. Next, even if you know PyTorch, you have no idea what the dimensions of the tensor are. Like here you can see they're free dimensions, but what does each dimension represent? In essence, what are we going from and what are we going to? Then, there's this thing, what is mask doing? We see mask could be none, but what's the type of mask when it's not none? So really we have no idea about what's going on or what any of these things are. Finally, why are we returning a view of X? This is kind of a weird thing to return. We're obviously subtracting a dimension. Why are we doing that? So let's look at how we can make this a bit more understandable, at least. So as I said, we'll do the type hint and the document string. Already this makes this a lot easier. Now I know this is a PyTorch tensor we're passing in. Mask is also a PyTorch tensor, and we're finally returning a PyTorch tensor. So, and then here, and even more importantly in the document string, I now list the exact dimensions of the tensor I'm passing and what each stand for. B is going to be the batch size, L is the length of the time series data, and M is the number of the time series values passed. That helps clarify, even that brief document string helps clarify a lot about what's being passed. Similarly, now we know why we're subtracting a dimension, and in the end we're just returning a tensor with a dimension of the batch size and the length. Yeah.
Could you tell us if type hint is available in Python 2?
2.7, I'm not sure about the support at the moment right now. I think you can do type hints, but I don't think it's as robust as in free. There's a whole typing library in Python free. But yeah, that's a good question. I do everything in Python free nowadays, so. But yeah, that's definitely good for 2.
Python 2 end of life was last month.
Yeah. Okay, so let's look at kind of the more overall view. This is probably going to look really small, but another thing I can add is I like to add just, is that not coming? Oh yeah, it is. Just a simple explanation of the model, maybe the author wrote it and maybe a link to the paper would be really helpful there in the doc string there. Obviously we add this doc string and type hint for the forward method. And then we also, I really like to describe the dimension, why we're reshaping to a new dimension, because now the person can then say look up that module and it's pretty easy to see. It's not really entirely necessary, but I do think it helps clarify, particularly if someone who might not be familiar. Okay, so that's kind of the first section on doc strings and type hints. My next section is unit tests. So my point is write unit tests. I think we've all been in that situation where as machine learning researchers and data scientists, we just want to train our model now, and we want to get our paper out and our results to the stakeholders, but we don't want to write a bunch of time-consuming tests to check, unit tests to check the logic. But really this is very important because the sooner you catch bugs, the less problematic they are. So it's a lot easier to catch bugs early with a unit test than start training, have your results be terrible, and then spend days parsing through your code wondering why are my results terrible when a simple unit test might have caught the bug initially. Also, there is a cost factor. If you're using a lot of TPUs, your cost can go up really quickly. I won't do all the math here, but from that example, you could see you could easily wind up with a giant bill just from starting a bad training session. And finally, as you extend your code, you want to know if any of your changes are going to break your existing code base. So basically, it's important to write unit tests. So let's look at how we might do this. So first, even in the setup phase, I basically check that the model initializes, which is nice because sometimes it won't. Then, I will test that the forward method runs and the correct dimension is returned. It's important to just check everything that your dimensions are working. And this is one of the, I think, most important ones that I don't see people do a lot, even people who do unit tests at all. I really like to check the intermediate dimensions of my model because often with deep learning, you'll be working with models with many different steps, many different layers. And oftentimes, actually, if your dimensions are incorrect, a lot of times they won't crash. They'll just keep running and then you'll be wondering why they're not converging. So it's really important to write your code in modules, as I'll talk about in a second, and then test those that those correct dimensions are correct for the modules. Finally, here's a test for data leakage. Basically, this model uses a masking mechanism, so of course I'm hyper paranoid about accidentally leaking my train and leaking subsequent time steps and using them for forecasting. So I wrote a very big test, and you should be too because no one wants their results invalidated. So my next point is going to be raise errors in your code. You're going to be like, are you crazy? Why the heck would I want to raise errors in my code? Aren't I trying to fix errors in my code? Well, again, it's a lot better to raise an error early than have your model continue training and for you to wonder why it's not converging. So for instance here, if the loss ever becomes nan or infinite, I want to kill this immediately because that's going to corrupt my model weights and obviously my result's going to be invalid. This was actually happening to me a fair amount. I was running and I was having these nan losses and I would come back an hour later and I'd see my weights were entirely corrupt, and that's just wasted time. So it's much better to kill the process immediately. Of course, sometimes you do everything right, but then a bug pops up in your training loop. Can you spot the bug? I, of course, couldn't. You probably can't since the screen's really small, but in any case, essentially I was logging just the loss to weights and biases instead of the actual running sum loss over this thing, and so I essentially spent days wondering why my loss curves were looking like this. So basically, this was obviously a very stupid mistake, but at least myself, I often make stupid mistakes, so maybe you don't, but if you do, let's look at how you might avoid this. So obviously peer review can sometimes catch some of these bugs early on. Then again, it might not. Some peer reviews kind of quick, but it's always a good idea to do peer review early before you actually start running your experiments. Next, better variable naming. I should have had something like final loss or total loss. That could have helped clarify things. More modularized code could have also definitely helped, I think. As you could see, I wasn't really returning anything, and I was just logging directly from my loss loop to to weights and biases, which I'll talk about later. And then finally, better automated tests. So let's look how we might do this. So here's kind of a refactor for a single epoch. Notice even now I do type hints still. I didn't actually include the doc string. There is one, but that would have pushed the code off the slide, so I actually cut it off for here. But you can see I did end up renaming this to total loss, which I think is better. Total loss, and then I end up returning. Wait, actually that should be total loss again. That's not the final one. I just drew this up just for this slide, but you can see how easy it is to miss your variable names. So then how do we actually test this though? This is actually a really great case for like kind of dummy model. So here, so you'd be like, might be like, why would I want to create a dummy model? But it's actually really useful because then this, essentially since this is just doing returning ones for every input, then now we can essentially just pass this to the loss training loop. And since it's always returning ones, we should always know what the loss will be. And then we can write a good unit test of what the loss, that returned loss from that previous function should be. And then that will hopefully fix, some of those bugs that could pop up in your training or validation loops. Okay, so now let's talk about designing modules for extendability. Basically with this, you always want to design modules for reuse and to add functionality down the line. This is kind of just good software engineering practice, but I see a lot of data scientists and even machine learning researchers often don't do this. Then the next big thing, I guess, is just create, do you want to create, generic classes for shared functionality. And of course, smaller modules and smaller functions means they're easier to test, which goes hand in hand with kind of the unit testing points I just raised. So this is going to be really hard to see, unfortunately. So I won't spend too much time on it. But basically, this is kind of a just generic data loader class. This is probably really simple anyways if you're a software engineer, but as I said, I don't see a lot of people doing this. But so here you can this data set in PyTorch can return variable length sequences of any length. You can pass also any type of scalar to it. Sometimes you might want to scale your data, sometimes you might not want to, so it's nice to be able to have a scalar that you pass to it. And then again, throw errors wherever you can. This was a big help because now if any bad data comes in, it throws the error right here rather than even entering the training loop. Because obviously if I have any NaN values and they make it to the model, that's just going to cause NaN losses. So that's so just always think about where you might want to catch things before they become bigger problems. Next up, creating generic wrappers. This is maybe a bit more advanced kind of software engineering, but I really like using abstract base classes, mainly because with an abstract base class, you can easily subclass it for extended functionality. And it makes it really easy to organize a bunch of different types of models, which might be in a bunch of different frameworks. So let's look at this. Here's a generic abstract base class for a time series model. Basically, I'm going to handle all the functionality I want across models. So for instance, here, all my models, whether they're scikit, PyTorch, TensorFlow, I'm going to probably want to resume from a checkpoint. So that's what this is doing here. Similarly, I'm always going to want to have my storage client here, and we'll talk more about this when we talk about the data versioning section. But this makes it very easy to essentially, upload your weights and upload the results of your experiments. And but the major point here is just that it's a functionality that will be shared across models. So that's why we'll put it in the abstract base class. So then we would subclass the abstract base class for additional functionality and features. So specifically for the PyTorch model, we have this PyTorch specific device thing. Is CUDA available? Is my GPU available? We want to instantiate that for the model. We'll also implement this abstract method to load the model because, of course, PyTorch, the way you load a model is actually different than it would be for other frameworks. But that abstract method really organizes things nicely because essentially now every model will implement that abstract method. So yeah, just more PyTorch specific stuff here. Another thing I see a lot is what if I did this instead of this or swap this layer for another layer. This is a really good thing to think about, and you want to keep that in mind when you're designing your classes. So one of the things I like to do a lot is you use these layer dictionaries that essentially map that where you can just, and I'll go into this a bit more when I go into the JSON config files, where you would take a string, you map it to a layer class, and then you instantiate it with a dictionary of parameters. And if you're not familiar, keywords is very useful in Python for this reason. You can essentially just pass a dictionary of values, and then those values will take on the names of whatever parameters are from the class or the function. And in this also, I really don't like if-else statements, so this reduces the need for a lot of if-else statements. Okay, part 2, tracking experiments. So, for people, I guess, who are just kind of smaller brain like myself, I like to have a very clear JSON configuration file because I just can't keep track of it otherwise. Other people like to just pass in all their arguments as with an args parser. And then other people might like to just have comment things in out for different model configuration files. Of course, the really smart people that can remember everything and what exact hyperparameters they use will just have a big notebook and uncomment and recomment their hyperparameters in and out because they can just remember all of that. But for people like myself, as I'll explain, you know, the JSON config file I think is really the way to go. So I will just talk about args parse for a second because I know a lot of people really like that. Yes, it's a nice command line interface and it is intuitive, but you know, in the end you're often typing your arguments again and again to the command line, and then, you know, and then this also results in a lot of if-else blocks. Plus, unless you're actually diligently copying and pasting those arguments into some kind of sheet for tracking, it leaves you with no like concrete file that you're actually using. So this is why, at least myself, you know, being small brain, likes to use these JSON configuration files because they're very neat and clear in what parameters we're using for each training session. So here's actually an example from Allen NLP. That's how I got the inspiration from this. Unfortunately, I know this is kind of small, but basically here, you know, you have different parameters for the data set reader, you have different parameters for the tokenizer, and it's all kind of laid out in a nice JSON format. So I think that's a really nice way of doing it. This is a very complex configuration file. I'll actually show one of my files, which is a bit simpler. And again, like these model parameters are going to be passed directly as keywords to instantiate the model. Similarly, I showed you the CSV data loader before, and essentially these parameters like forecast length and other things are going to be passed directly to the data loader. And one of the things I really like about these is now we have actually a concrete file that marked what this experiment was. So I might lose some people here, but I really want to also show how good software engineering can actually enable new ideas for new experiments. So there's a variety of techniques for few-shot learning. One of them is gradient-based methods, where essentially you have an inner loop which trains on a specific task, you have a distribution of different tasks, and then you have an outer loop which then basically, after each inner loop on a task trains, it basically backpropagates how well it did in learning just from just a few examples of that task. So and one of these algorithms is actually called MAML, which is just model agnostic meta learning, and there's another called Reptile. But the coolest thing about them is they could essentially take any base model and any distribution of tasks and then train a model, and then train that model to be able to do few-shot learning. So being able to train from only 5, 6, 10 samples, because it essentially learns to learn over a distribution of tasks. So despite being model agnostic though, you'd think, why has it only been really used on imaging tasks? Well, the answer is actually, even though the method is model agnostic, the code is task dependent, which is kind of odd. So how can we make this actually model agnostic? Well, we can create a model agnostic wrapper. So this is actually one of the things I've been working on for the Allen NLP library. But basically, what this is doing, this is subclassing the trainer in Allen NLP. And so basically we'll have a model, then we'll have some base model, and then we'll also have a meta-learning model or a meta-learning method. We'll also have a list of training data sets, similarly a list of, test data sets, and, a certain number of meta batches we use, and a certain number of inner steps. Again, meta learning is kind of complex, so I won't really run through how all that works, but the point is that, good software engineering and these kind of generic wrappers can enable a lot of cool new experiments. So, another tool I really like to use is weights and biases. You might have heard of it before, and you saw that I was logging to it before. It's free. It's free in most cases. So I'll just quickly break my slideshow to show you a couple cool examples of this. So basically here what we'll have is basically info from, I'll zoom in a bit since I can actually zoom here. So we have, it automatically records the data of the training session, what the system was, and it works really well with those configuration files I showed you. So here are all my configuration parameters that went into this specific experiment, which is nice. We can then see, the loss graph, and obviously after fixing my various bugs, it now actually looks like it converges. Similarly, here's the validation loss. The validation loss seems to go down until it overfits, it looks like. So, anyways, as you can see, it makes it very easy to kind of track your experiments here. Similarly, like, you can track multiple runs, see how well they do. There might be some problems with some of these methods, but you kind of get an idea how you can easily click on and compare multiple runs. I did have another example of that too. So example report. So you can also recreate reports really well. So here's this isn't my report, but this is someone else's report on transfer learning. You can easily take your various runs and kind of look at them. So there's fine tuning an inception net, etc. I won't spend too much time on this. Finally, they have a new thing called sweeps, where you can easily sweep across a bunch of different model hyperparameters and see how well they influence your run. I don't know if that's going to load. Anyways, yeah, the internet on Adam's phone might not be powerful enough to load this dashboard, but so I guess I'll just return to my main slides. But as I said, I'll post the slides later so you can click these links and play with them. Okay, let's move on to managing dependencies. So with managing dependencies, it happens all the time. You see some cool repo on GitHub, and then there's even instructions on how to run it, but then you follow the instructions, and then you're saying you're hit with all these dependency issues. So everyone knows Python does kind of have these long-standing issues with dependencies. It's of course even more of a problem for machine learning because you can't rerun past experiments, or it could even change the results of the past experiments if it doesn't crash. So now I'm going to talk about some of the solutions. So Docker containers, you've probably all heard of Docker before. It's a great way to move to because then you have a managed environment. However, there's still some best practices you should use for it. Really be explicit in your requirements.txt file that you put into your Docker container. Obviously, second, you want to store your Docker container digest in your configuration file. And another nice thing about weights and biases, it will log it automatically. So I do see some bad practices with Docker though, so this is a good example of how not to do a Docker file. Why? Because if you're just pulling the latest of an image, it will create the same kind of dependency problems, or it could potentially. It's still probably a little bit better, but this could easily still have breaking changes. Similarly, if you're cloning a repository into your Docker container, you don't just want to clone it because now it's going to be whatever changes are just going to pop up there. And yeah, those are kind of the major points with that. So let's look at how to do a Docker file a bit better. Basically, you have a version number, have explicit requirements. I'll show the good requirements txt file in a second. And then finally, if you are cloning a repo into your Docker container, use a commit hash. And ideally, you'd store this commit hash in your configuration file or somewhere else. So here's a good example of requirements.txt file. We have explicit version numbers. I know these are a pain to put in. I hate putting them in, but it enables me to know exactly what versions were used. Then we will group similar dependencies together in the requirements file. Some things, I probably should have added a version number for this, but PyYAML might not break it, but really you should have version numbers for everything. Okay, let's move on to data versioning. So I think we've all had that thing, we're basically trying to rerun some model code, and of course we get a file not found error, and people come to me like this all the time, and I'm like, oh, is this just your first time with these issues? So how can we better manage our data versions? In summary, data versioning is really complex, and I'm already at 40 minutes, so I'm not going to delve too deeply into it. But basically, the best way is to store immutable snapshots of your data on the cloud. So basically, your data should always be stored and versioned accordingly. This might not be possible for like really large data sets. So for those, you really have to kind of weigh it out, the cost of data storage versus the reproducibility aspect. Similarly, there are times when you might want to just include all your pre-processing in your actual code. I actually do this for some of my flow forecasting because the pre-processing literally takes seconds, and then that way I can actually do my pre-processing as a parameter. Obviously, this would be a very bad idea if you're pre-processing like terabytes of large video data or something, but for small files, you might want to just consider having your pre-processing be like a parameter and run everything from the raw data. So some more basic tips. I already kind of, oh yeah, don't pass things around by email or Slack. You'd be surprised how often this happens. Always have like I guess a definitive link pass around the link to the file in the cloud instead, then they can use it from the raw data. Similarly, object versioning is very nice. It's very easy to accidentally overwrite files on the cloud. And then, yeah, the rest you can probably just read through and look for yourself, but standardize things, record timestamps, absolute paths. Yep.
What's your opinion on using pickle?
Yeah, in general, I don't like using pickle that much because it can create like hard things that don't reload very easily. But I guess my approach, if you did use it, would be to obviously have your exact like configuration and maybe like include some other metadata about what exactly you're dumping in the objects and stuff.
Yeah, I meant for like things that are very, obviously very nuanced and that sort of thing.
Yeah, I mean, so I think like if you're just doing it one-off and you're not planning on using it again, it could be acceptable.
You would use it regularly?
Yeah, no, I wouldn't use it regularly. So yeah, finally, just I see a lot of people don't really take time to write code to download and interface with the cloud. Obviously, this is something your data engineering or other team could help you with, but you want to have loaders for getting your storage, for instance, and then you also want to have this is my upload function, so as my model runs, it will automatically upload my weights, so then I can easily resume from a failed checkpoint and just terminate the instance without having to worry about that state and everything. So these are just kind of nice utility functions to have. Similarly, it's really nice to be able to just have a function that easily downloads from either can run with a local file path or a URL. So this is actually from LNLP, but it's really nice because if the file is a URL, it will take it and cache it. If it's a local path, it will just run it. Those are both useful.
Looks like we have another question.
Oh yeah.
Have you compared what you're doing here to something like MLflow or Delta Lake, or MLflow for model versioning, Delta Lake for data versioning?
I haven't used MLflow that much myself. I have used Kubeflow before, but I find Kubeflow pipelines to be kind of somewhat complex and have like a high learning curve, and they're also mostly based out of notebooks, which, as I said, I don't really like as much. But yeah, I do have to look into MLflow, I think. So I guess my core takeaways, again, I kind of beat this a lot tonight, but good software engineering enables reproducible experiments and more importantly, extendable experiments that you can then build off of and share and collaborate with others on. Focus on your code quality. That should be first and foremost. Write unit tests. Hopefully I instilled that in you from all those examples. Configuration files, great if you can actually remember all your hyperparameters and what things went with what session. Most people can't. And then, finally just define your Docker files with explicit versions. And then, for data versioning, it's complex, but figure out your data versioning kind of strategy early so that you can then that it's easy to build off of and you can run reproducible experiments. So there's some other good talks here. I really like Joel Gruss's talk on why I hate notebooks and pretty much agree with most things out of it. Another good talk on like how not becoming non-data scientists, made him a better data scientist is there. There's also, this is a good blog on designing good Docker files. And I think LNLP in general is a really great repository that kind of combines the cutting edge in software engineering with the cutting edge of deep learning and NLP. Finally, yeah, I didn't talk too much about meta learning or transfer learning. I did bring them up. I did also bring up a bit about deployment, but not in detail. So I do have a blog and I write about some of those topics there. You can also have me on LinkedIn. I'm also on the Slack group, so if you have any additional questions after our Q&A, you can just ping me on there. Anyways, looking really forward to any additional questions you might have now.
If I see your hand, I'll try to run mic to see how well it works.
For data versioning, by that do you mean like you've got like a new set of data that you're trying to train on, or is this like different stages in the cleaning process?
Yeah, it could be either. I mean, really, like this could apply both as new data comes into a pipeline, so like you get more results, or as you pre-process and run different stages of pre-processing and stage it. But that's why I think object versioning is a really good idea. So even as more data might come into a table, you could still have that version, kind of almost version control of the data to reproduce your experiments. And of course, some of this goes hand in hand with like when to retrain a model, but I didn't really have much time to address that. But that's another good topic for another time.
I had a question about your testing with Flow.
Yeah.
So, do you normally, like, in addition to like using like unit tests, like default out of like, Python or like PyTest is like output of like HTML, do you typically like have a natural break in which you're like, all right, I should probably now swap over to like test this? Or that's usually like where I find that, after like 5 hours of just like straight being in the flow of it, you're like, all right, I don't want to break out of it and now like have to test all of this.
Yeah. I mean, it depends. There's sometimes when I'm really in the flow and I don't really want to break out and test, so I kind of have to force myself. But there are times when I just do honestly want to write the test because I'm worried something might be incorrect and I don't want to start training knowing something might be incorrect, because I guess I've become kind of paranoid about stuff being correct now. So.
TDD, Hey, thanks for the talk, by the way. It's really good to sort of zoom out and capture these aspects. So data scientist teams are structured differently, I think fundamentally differently sometimes from software engineering teams, right?
Yeah.
It takes some time for a bunch of data scientists to, for example, converge to the kind of interfaces that you showed, right? If these are my classes, these are my interfaces. It takes a lot of time for a group of data scientists to sort of agree that this should be, and initially it seems like wasted time, right?
Yeah.
Product manager just wants to know, hey, is this even possible?
Yeah.
Should I even be considering it? So all data scientists want to do is run and prototype something. So what are your thoughts on where is the threshold? When do we decide, okay, this has become complex enough to sort of step back, design this properly, and then move forward instead of just everybody going on in their own direction?
Yeah, that's a really good question. I mean, it's definitely hard when you have like external pressure just pushing you to get a result. But I'd say like from the beginning, even if you have a certain deadline, it's good to think about just classes and modules. Maybe not write out all your tests then, because if you have like a strict timeline, but just start thinking about classes and modules that can be maybe abstracted. But yeah, it can definitely be hard when you have someone that's, I need this result at this time. So you kind of have to, I guess, just weigh and try to balance that as best you can.
All right, thank you for the talk. I'm gonna have to disagree with you on one of the slides though. The truly big brain thing to do is to not write any comments in your code and then leave the company.
Okay.
Jokes aside, I appreciate your talk. Hearing from your experiences and from my own experiences working on machine learning and data projects, I get the sense that data scientists could really benefit from some formal instruction in software engineering. Do you think that's a possibility in the future that it'll become more common to see data scientists receive training in how to think like a software engineer, or do you think that's still far out?
Yeah, I definitely think we're moving in that direction. I think almost like maybe to a ML machine learning engineer is almost kind of the synthesis of those kind of two titles. I think it will be more common to like, I guess, have more well-rounded people. For a while, I guess there was kind of two separate camps. You were even in software engineering or statistics and machine learning, but now we're seeing more kind of the merging of the two already. So, and my guess in the future it becomes even more so.
Yeah, as I walk I totally agree that as teams grow larger and they start to cross-mingle between data engineering and data science, it has been possible. And it's a big question that I've always asked, like, what would it take for data scientists to actually write good code as a person who sometimes deploys data science code? And it's like asking what would it take to make it easier to do things the right way from the beginning, and those things are really good conversations to have with your teams. Please do all the things you said.
Next up. So I have a question about, you mentioned using JSON as storing all the inputs. How exactly do you keep track of different JSON files? Because there are many parameters in it. So do you use the file name or some other type of way?
Yeah, so the JSON file is really good to use with weights and biases. So that training run is then, that entire JSON file is stored with weights and biases as I kind of showed up there with the model results. I also do a second step of archiving it, so that JSON file and then the training run are given unique IDs, like the weight file is given a unique ID. And similarly, the JSON file, that matches the JSON file. So then always that one JSON file will always be associated with those weights and those training run results.
We have time for one or two more questions, and then we can converse amongst those, or run away, or those things. Who's got more questions? Or 0 more questions, that's an option too.
Why are you using Wandb instead of something like TensorBoard or TensorX or any idea?
Yeah, I mean, TensorBoard is good too, but I like weights and biases because, as I said, it works really well with the configuration files. It's really easy to log JSON to it. It's also easier, I think, than TensorBoard to like graph and group multiple experiments over time. And I just kind of like its simple interface.
So do you use any like packages for helping with the data versioning, or just like writing your custom code? Like, have you tried out like Git LFS or like DVC, and what's your experience with them? Yeah, I've used data version control a bit. I think data version control just kind of somewhat pushes off some of the problems with data management though. So I actually prefer kind of writing my own custom stuff. Because, you know, with DVC, it's nice, it uploads it, but you still run into those same problems if your data is very large and you have to version, and you want to version it. So.
Was this, were you not? Okay. I feel like I've done pretty much everything that you said not to do. Particularly like the argument stuff and like, I don't know. So I guess, do you have any recommendations for how to like learn how to do some of the stuff you said? Because you mentioned kind of like modularizing code, and to me like that sounds cool, but I don't exactly know how to do that. So I'm curious if you have like any recs on that.
Yeah, I mean, I think it really does start with just like object-oriented programming and kind of learning some of those patterns and how to use Python classes, and then maybe learning a bit more about like, you know, how to structure things. Because have you taken object-oriented or, okay. So that's always a good starting point, I think, and then kind of learning those common software engineering practices and slowly kind of merging the two, your stats knowledge and software engineering together is good.
Thanks everyone. So that's a really good segue into what our next month's talk is going to be. We're going to have, I'm Sarah Saperstein. I work at Mass Mutual. I'm one of the co-organizers of this meetup. Next month, we're going to have workshop tutorials in collaboration with the Learn Python Programming Meetup, and we'll have, I think, 3 tutorials on Python from kind of beginner level to more advanced. So we will answer those kinds of questions in that event. So let's thank Isaac again for the talk.
Just want to give one more announcement. We're always excited to have people give us ideas, things you want to know more about or want to talk more about, or if you don't think you have a good talk to me, I can convince you otherwise.